And a covariant vector bundle means I have a group action on X, and this is a lift of this group action to the total space of the vector bundle, so that in the fibers act by linear operators. Like, for example, if I have a smooth manifold and it has a tangent bundle, if I have a group acting on the manifold, it acts on the tangent bundle too and acts by linear operators on the fiber. So it's an element in here. And this is super. This in fact, you think, well, this is very abstract, but this is in fact very, very physical, because how you should think about it, it's you think of X as we're very tired people. We only do low energy physics. So we somehow try to keep it not too intense. And so the moduli spaces in question typically for us are like you have some part of the physical system, and you'd like it to be in the absolute minimum of energy. Like with these instantons are really connection that really strictly minimize the Young-Mills energy in given topology. And then so this is your X, and then this is a connection, define some differential operator and so forth. And so you can ask, in this background, what is like the lowest state, or some kind of, let's say the lowest eigenstate of this differential operator, right? This would be so. There's some vector space, some vector space that depends on your point here. So if you look. Right? Yeah. So here X, a point X is that background. Yeah. A point in X is some particular connection. Right? Or you put some part of your physical system, you put at the minimum. And then you can ask, well, maybe in that background, the rest, what would be the lowest eigenstate, or maybe have several eigenstates? It'll be some vector space that depends on X. May not depend on the continuous way I wrote it down. But again, in algebraic geometry, it's super suitable to analyze the fact when this is not a bundle. So this is I wrote the case. Suppose I have typical physicists say, well, the lowest state is just a vector, one vector, and so then it'll be like not a vector bundle, rather a line bundle. So it's some complex line that varies from point to point, and then this is. But that could be a vector bundle. Could be, in fact, if the situation is supersymmetric, then you have something bosonic and something fermionic, so it'd be like a difference of two vector bundles. Make sense? And if your group acted on X, then will also act on the total space of this. Like I said, may not be a bundle. We'll talk about this in a second. But particularly, you can imagine that this is a bundle. It's like a state of, maybe there's some matter. That is just connection. And there's some matter that has to obey some differential equation, basically Dirac type of equation. And you can ask, what are the actual zero modes of that Dirac operator? We find dimensional space. It depends on. So okay, so that's the definition. And then in topology, you just take an arbitrary complex vector bundle. And you take it with the operation that has the operation, so it's a vector bundle here, has operations. You can take direct sum with two vector bundles. You can take tensor products. You can take other tensor functors. You can take, for example, the exterior square, or the symmetric square, or any tensor power you want. So this is like, this makes the K group a ring with some additional structure. People call it a lambda ring. So, like, okay, so you should think of this like this. So if equivalent K theory is a generalization of representation of the group G. So in fact, if your point, you can always take X to be a point. It's valid. And then all there is, a vector bundle over a point, well, just a vector space. And the G equivalent vector bundle over a point is a representation of the group G. And then in representations of a group, there's all these operations. And in fact, you consider a ring of virtual representation means a difference of two actual representations. But then the vector space, now if you have a group acting on some base, then you can have a vector space kind of depending on your variable. And so that makes this a coherent K-theory. Okay? And so now you can define them. You can define there are two definitions. One is topological, and one is algebraic. In one case it's a topological space, and you consider just complex vector bundles with these operations. If it's an algebraic variety, you can consider algebraic vector bundles. Again, algebraic vector bundles, again, an algebraic variety whose maps to fibers over your variety with vector spaces. The operations are linear with respect to vector spaces. And then in algebraic variety, in algebraic theory, there you can further kind of break it in further. You can consider the K group of really vector bundles. Or you can take coherent sheaves. And these are the same if the variety is smooth. So in fact, for instanton moduli spaces, all these notions coincide. This is, but in general, these are three different things with three very different things. And so what is a coherent sheaf? The coherent sheaf is well, this is only one lecture. It's not the time for a course in algebraic geometry, but you can imagine that you can have a family of vector bundles, a family of vector spaces that jump. And jump in a certain very precise way. Like for example, suppose I have a map from so suppose I have two vector bundles. So still on X. So on X, I have a map between two vector bundles. So I have maybe V1 goes to V2. And then it can be that this map, for example, it can be the case that this map degenerates. Like for example, it could be like for example. So what is the where's my word? So what's the maybe the first example of a line bundle is if I take the very first variety, the very first example of an algebraic variety is projective space. So say Pn. Over that, so this is the set of lines in Cn+1. This is complex projective space. And over that, there's a canonical line bundle, namely when the point of the fiber over a line is the line itself. So this is, you should imagine, so this is maybe, if I draw a picture of P2, P1, so this is the set of lines, and then you can say, well, if the fiber over the corresponding line is the line itself. So the total space of this is the blow-up of the plane in this point. And so that this bundle is called O of -1 because it doesn't have any section. Right? I mean, there's no way to have an algebraic map that assigns for that this, well, anyway. But the dual bundle has section, namely, what's the dual bundle? These are linear, the dual bundle are the linear functions on this line. And if I have any linear functions on the plane, that will induce linear functions on every line, and so that would be a section. Right? So to say it like this, so if I have now projective space. Oh no, I have to wet this. Hold on 1 second. What are you guys doing? I ran away for a second and you somehow. So if I have, so if I take Pn, and that has this, so a point in here is given by homogeneous coordinates x naught up to xn, and each of these xi's, it's a linear function on the Cn plus 1, which so these are all sections of 1. And so then I have, if I consider, I can take a map from the trivial bundle of rank n going to O of 1, given by the coordinate x1 through xn. Right? And so this map is surjective except at the point where, so this is not surjective. So this is n bundle of rank n going to bundle of rank 1. Next surject, not surjective. Exactly at the point, just 0. At this point, exactly right. So this, if I take the quotient of this by that, what I'm going to get is so this is my Pn. And over that point, the point 1, 0, 0, 0, I'll have a one-dimensional plane. You know, I wrote a complex plane. I should have rewritten the line. So just over that point, I just get a line, and I get 0 everywhere else. Right? So it's a family of vector spaces that is not continuous. It jumps, but it jumps in a way that it's a quotient of one vector bundle by another vector bundle. Now, if variety is smooth, so there's something like this, which is a quotient of vector bundle by another vector bundle. That's called coherent shift. And if variety is smooth, then in fact you can continue this to resolution. You continue to resolution. And if it's and so in other words, if I look at the kernel of this map, then I can write an exact sequence of vector bundles that in fact so there's okay, well, actually I skipped over a point, and then in topology you don't need to impose this relation, because if you have a sub bundle, like if you have a in this picture you have a this is since you have a line in this picture, you have a line over every point of P1. You have a line itself that is a sub-bundle and trivial bundle of rank 2. So in topology, you can always, if you have a sub-bundle in the bundle, then you can always make it a direct sum, because you can introduce a remission metric, take an remission. So if you take an remission perp of this sub, that will be a complementary bundle. So every bundle you have a sub, you can write your ambient bundle as a direct sum. But in algebraic geometry, that construction doesn't work. So if I need a Hermitian metric to write this perp, and so this in algebraic geometry you impose the condition. If you have a bundle and you have a sub-bundle, so this means this inclusion of a bundle here, such that the quotient is again a vector bundle, then you impose the relation that the class of V is actually equal to the class of V1 plus V2. So that's the relation you impose. And so then more generally, if you have an exact sequence, a longer exact sequence means the kernel of one map is the image of the other. So the kernel of this map is the image of the other. Then, if you have any coherent shift on a smooth variety, so by definition it starts as a quotient of one vector bundle and another, but the kernel of this map you can resolve by another bundle and so forth, and by Hilbert syzygy on a smooth variety of dimension d, this will terminate after d steps. Like on this Pn, this will be terminated after n steps, and this is in fact kind of an important resolution to which we'll get. And so okay, that's the definition. Definition is that in topology you take complex vector bundles with the operations direct sum and tensor product and other tensor operations. In algebraic geometry you can take, let's say on a smooth manifold, you can take algebraic vector bundle modulo these relations with the same operations, and then you can also talk about the K-theory of coherent shifts. The coherent shift is by definition, like I said, it's a quotient, or algebraic geometry say co-kernel. Okay, so it's a quotient, it's a co-kernel. Right, so that's except if you have again on a smooth manifold, on a non-smooth manifold, there's no way to tensor multiply. So if you have like on a smooth manifold, any coherent shift will be resolved by vector bundles, and then those you can tensor multiply. But if it's just a singular variety and you have a coherent shift, there's no way to tensor multiply. It's not a ring. You can multiply coherent shift by a vector bundle, but you can't multiply two coherent shifts. And so what are the basic properties of this equivariant K group? So the varieties we constructed, so remember Nakajima-Quiver varieties, they were already constructed as quotients by a group. So we had some variety X, but in fact was a quotient by a group. Means there was some pre-quotient, maybe call it X twiddle, that mapped to X, and the fibers of this map were just actually the group itself. That clear? That was the construction. It's like the group. Yeah, that's a quotient. So I didn't prove it. It's an exercise to prove that in fact for Nakajima varieties, this is in fact this action of this. This was the stable locus, and this action on the stable the action there was the semi-stable locus, and the action on the semi-stable locus is in fact free. That was that's a part of one of their exercises. And in fact, by the way, there'll be no new problems for today from my side. And so if you have like a second chance to go over this problem. So anyway, so then, anytime you have a situation like this, then you have, by definition, this makes this a G bundle over X. If you have a G bundle over X, means if you have a transition functions given in your bundle, you can think of this as given by transition function. If you have a G bundle over X, you can any representation of your group G. So if G acts, so if G goes maybe the representation of GL some space V, then you can use the same transition function to make a vector bundle. Like for example, if you take for projective space, this is a quotient by just C star, and if you take defining representation of C star, you're gonna get this O of -1, if you take the dual to the defining representation of C star, you're going to get the dual bundle. For Grassmannian, if you take Grassmannian is a quotient by GLK, Grassmannian of K planes. If you take the defining representation of GLK, of course, you're going to get this tautological bundle, namely, so the fiber over a given point in the Grassmannian. Given point in Grassmannian is some k-dimensional subspace. The fiber is the subspace itself. So if you take defining representation, this is what you're going to get. If you take the dual to the defining representation, you're going to get the dual bundle. Namely, the fiber over a given subspace is the dual space. And algebraic, so in representation theory, the first thing when people come to representation theory class, the first thing I tell them, representation theory is basically like a linear algebra, except you have to distinguish representation from the dual representation. In linear algebra, they teach all vector spaces are the same. In fact, not. So the representation and dual representation are very different representations. This is even more true in algebraic geometry. A bundle and a dual bundle are just completely different things. So O of 1 and O of minus 1, it's like the opposites. Okay? One has sections, another doesn't. So okay, so this is so this gives you a supply of vector bundles. And in fact, for Nakajima Quiver varieties, it is a theorem which we will explain. Maybe I'll explain it later over time. And this is in the end the last nail of this was put in by McGurty and Nevins. This is the last nail in this coffin. Is that in fact the K theory, the K theory of X is in fact generated. Generated in the sense that you allow yourself also exterior powers. So so this is in the sense of lambda rings, means you have tautological bundles and their exterior powers is generated by tautological bundles. I'll explain how the proof of that goes. And not only that is true, in fact, it's all of them, the algebraic, the topological, it's all the same. And in fact, if you take the Chern classes of these bundles, that generate the integral cohomology. That's integral cohomology. So if I have a vector bundle, that is a way to associate cohomology classes to that. Namely, I choose a connection on this bundle, and the curvature of this connection defines differential forms. And so that's this Chern-Weil homomorphism from K theory to cohomology. And in fact, so this generates the whole thing, and I'll explain how this goes. But what? No. What? No, X is Nakajima variety. This is. No, if in general this is never true, because you can take you can take a trivial quotient, like you can just take your variety, multiply by G, take the quotient, and then this is the first statement about the covariant K theory I want to make is that in this situation, so maybe let's add some equivariance. Maybe there's a different group H acting on X, and then this is in fact maybe these two commuting groups act here. Let's just make them commute to simplify things. This is anyway what's happening in the varieties of interest. And so then the first thing is that if I take H equivariant K theory of X, that in fact is equal to H cross G equivariant K theory of X. Check. That's the first thing. So a sheaf on a variety on the quotient is the same as an equivariant thing before. And the way it goes is that if I have a bundle here, I can just pull it back here, and it'll be a bundle with the action of G. What? Oh yeah, tilde. Yeah, sorry. Thank you. So, right. So if I have a bundle here, then I can just pull it back. It'll be a bundle with an action of G. And if I want to go back, I just take invariant sections. Right? If I want to know what are the sections over an open set, I take the preimage of that open set upstairs. It'll have some sections. I'd look at G-invariant sections. For example, if I want to know bundles on projective space, so e.g. K-theory, let's say, whatever, PGLN equivalent. So this is this. I want to know K-theory. Maybe I want to like PGLN equivalent K-theory of projective space. This automorphism. That is the same as GLN equivalent K-theory of Cn minus 0. This says I want a vector bundle here that is equivalent with respect to the additional scaling. It's just like a bundle here on which this additional scaling acts. Right. Now, okay, so this is, people say sheaves on projective space are the same as it's graded sheaves. What does it mean I have an additional scaling? It means I have a grading with respect to this extra variable, graded sheaves on here. So this is one thing. And then the second property, very important property in algebraic in K-theory is that right? So sorry, I forgot. This is the source. I'm talking about formulas, and in particular, there are two kinds of formulas. There are formulas of the kind. There are. So if I may, sorry, with all due respect, there are two kinds of formulas in this business, and I guess they both appeared in Seeberg's talk yesterday. So they're kind of integrals. And then there are box countings. And integrals, they come here because what does it mean? What does it mean to take, so if I have a bundle upstairs and I want to know sections over some open set downstairs, what do I need to do? I need to compute upstairs, which is usually easy. Okay, so this is okay in vector space. We can deal with that. We can compute upstairs, but then we need to take invariant sections. How do we take invariants? Invariants we take using while integration formula. While integration. So this is where. So if we want to know, if you compute something as a representation of a group, and you want to project onto invariance, you just integrate over the group. That's a basic fact. And then when you integrate over the group by while integration formula, you can integrate instead over maximal torus with some weight. And that's the origin of all integral formulas in this business. Right, so these formulas are just integration, just while integration formula slightly glorified, except the choice of the counter of this integration. So in fact, so this is we discussed in the previous lecture. There was when you take this quotient, you may have choices for imposing what stability condition to impose. You can choose different open sets on your pre-quotient, which you declare stable. And the choice of that open set, the choice of stability conditions, the choice of counter of integration. So that's okay. So coming back here. So the other very important thing. So if I have a closed set, so this is closed. Inside X. So this is so if I have a GIT quotient and I want to compute something, maybe like the Euler. So right. So maybe I should have said this at the beginning. The ultimate thing we want to compute is It's like the Euler characteristic of a vector bundle. Namely, ideally we would like to compute the character of the space of sections, but this is very hard. Instead we compute the character of the space of sections minus the character of the first cohomology plus the character of the second cohomology minus the character of the third cohomology and so forth, this Euler characteristic. And so the Euler characteristic of a sheaf that you obtain on a quotient via this procedure, you compute as the Euler characteristic upstairs, but then you project onto G invariance using contour of integration. That in this procedure, there has to be a choice that depends on the choice of stability condition, because it could be different stability condition. Like, for example, when you write this, there will be, with one choice of stability condition, the quotient would be projective space. With the other choice of stability condition, the quotient will be empty. So then this choice of stability condition is reflected in the choice of contour for integration. So that means with one choice you're going to get a non-zero integral, with the other choice you're going to get a zero integral. And so suppose I have a closed embedding. Then there is a push forward, namely if I have any coherent, so this is now I'm going to talk about coherent sheaf. If I have any coherent sheaf on X, on Y, I can just, so this means it's a module over functions. What does it mean to have a coherent vector? What's a vector bundle? Vector bundle is sections of a vector bundle is a module over functions. You can multiply by functions, and that module is locally free. Means on some open patch, it really is free because it's a bundle becomes trivial. And then a coherent sheaf is not a free module, but is a finitely presented module. It has finitely many generators, finitely many relations. These two vector bundles are the bundles of generators and the bundles of relations. And so if I have a module here, I can extend it by 0, and just to have this, there is a map. There's a push forward map. So in general, so that's this. And so then there's an exact sequence that says the equivariant K group of the closed set goes to the equivariant K group of the closed of the ambient space. This goes by restriction. So take away the origin, and that is 0. So that's exact sequence. So this it's like the analog of excision in K theory, and the kernel of that factor. So there's some kind of higher K group here, which we're not going to discuss. Right? So this is very important. This says that every coherent sheaf on the open set can be in fact extended to the sheaf on the ambient space. And everything on the ambient space that restricts to 0 on the open set, in fact, comes from here. Okay. So now we're going to apply this here. And so what was it said? That will say that this K theory, this is just the current K theory of just Cn mod out by current K theory of just the kind of the origin. Because this is my X and this is my Y. And so that says, well, this is just okay, every bundle. In algebraic geometry, it's a non-trivial theorem to prove, but true that every bundle over a fine space is trivial. I mean, topology is a trivial statement. So this is just representation. This is just representation of GLN. And here you kill some particular one. And so what do you need to do? We need to resolve. Maybe I'll do this computation. So we need to impose some particular relation. So what is this relation? So if I need to so I have maybe I'll write it in the box counting style. So this is my picture. Maybe let's do it for n equals 2, since this is already very representative. So this is my ring of polynomials of 2 variables. These are just monomials. Yeah, because it's equivalent. The fact that it's equivalent is trivially true. Yeah. That's right. This is yeah, true. Pasha, you're priceless. But of course, if it's an equivariant bundle, it's trivial because you just take its because it will be trivial. By definition, it's trivial on some neighborhood of 0. But any neighborhood of 0, since it's equivariant, you can just inflate it. So that's this is my ring. This is my picture of the ring of polynomial in 2 variables. And so this is the thing I want to, and this is the structure sheaf. So the inclusion of 0 is the structure sheaf of the origin. And this is something I need to find out what does this guy mean. What does this guy mean in terms of vector bundles on my projective space? And for this, I need to write a resolution of that object. How do I write a resolution? Well, first of all, there is maybe I'll write. So this is the guy I want to kill. And by definition, this surjects. If I take all polynomials, this surjects to that. So I'll just write C of maybe x1, x2. And the kernel, what's the kernel? The kernel is everything. The kernel is everything which is not covered by this. But so in particular, the kernel is generated by this and by that. Right? Yeah. I'm computing a resolution. I just want to know what is the so if I want to mod out by this, I'd like to know what is the relation I get here. And for this, what do? I have to resolve this sheaf by vector bundles, and I'm gonna get the no, yeah, actual compute actual resolution. So this is the kernel of this map was generated by these two guys. And so this is like, maybe I'll write it like this. So the kernel here is like maybe x1 times, maybe I'll just think this O, x1 times O plus x2 times O. But then it'll be overkill because this part will be covered twice. And so so this will be a kernel of this map, which is in fact generated by x1, x2 times O. And this is now an exact sequence. Is that clear? So you can imagine, so does that make sense? So in fact, you can imagine that something like this for any kind of monomial ideal, there's something like this. Is in 2-dimensional will terminate after 2 steps. In 3-dimensional will terminate after 3 steps. In d-dimensional will terminate after d steps. And that's in fact the proof of Hilbert's theorem. Because all the syzyges, or any sheaf, all the syzyges are semi-continuous. And so if there is a bound for all the torus fixed ones, then there's an overall bound. But what does this sequence say if we now lift it here? So what would it say? It say how we translate it. How we translate it there, and maybe I'll take the eraser. So in K-theory of projective space, it'll be say what? It'll be say 0. This is 0, because this is the thing that's supposed to die. This is, well, that's just a structure sheaf. Or P1. Maybe I'll write it O P1. What is this? Here I have 2 copies. two copies of my structure shift, but they are shifted by these two guys here. And so what is this canonical? This x1, x2, they're coordinates on my, maybe I'll write P of vector space, it'll be better. And then the vector space is my C2. So these are as an element in my vector space, they just come from, they're linear functions. They're in the dual of my vector space. Right? And then, but also as they're had degree 1 with respect to that scaling action. So what I'm going to get here, if I interpret everything canonical, I'm going to get the dual of this vector space, tensor of -1. And then here, I'm going to get the exterior square of the dual vector space times of -2. And so forth in general, but since this exterior will terminate, yeah. What? Say it again. Well, it's just you interpret what this map means. What is this sheaf? If you think of this, this is some vector bundle over C2. Now we make it a bundle over P, and that becomes this. Yeah. And so you get so in projective space you get a relation of the following kind, that this is if you denote this guy, if you denote O of 1, the O of 1 is a line bundle. Maybe we'll denote it. Is that okay to denote it little x or s or something? So maybe too many x's. Let's call it s. Maybe call it L for line bundle. It's an element in my K theory. And it says that this guy satisfies the relation of the kind that if I take kind of, and this is the trivial sheaf of rank 1, so this means 1 in K theory. So this becomes a relation with 1 minus L inverse times V dual plus L minus 2V exterior square. V dual minus so forth equals 0. That's the relation. Well, how should I think about that relation? That relation, if I now think in terms of representation of GLN, I should think of this I should think of V. Well, if I take GLN, take a GLN, a matrix in GLN is of the form maybe A1 through AN. And then when I think about representation, I think of a trace of this matrix in this representation. So I think V, the defining representation, is the trace of this matrix in this representation, this symmetric function in these variables. And then what does this relation say? And if I take exterior square of V, this is the second elementary symmetric function in this variable A and so forth. Then this relation says what? This relation, this is become like the standard generating function for elementary symmetric function. So this relation becomes the product of 1 minus L inverse times AI inverse. That product from 1 to whatever, that product equals 0. That's the character, yeah. So in general, so if you think of any, right, I didn't say this, if you have, in particular, you have among G covariant bundles, you have trivial bundles with an action of your group G. So the covariant, so there is a map from In other words, x maps to the point, and so you can pull back. So, pull-back map from a point that gives kg of a point. That is to say, just representation of g goes to kg of x. I know, but I already have it in my other hand. But I already wrote this in this chart. Okay. Anyway, so this is the relation. What does this relation say? This says, so maybe I'll this is when there's some saturation to this board, which means the electron has to stop. So this relation, so maybe no, this chalk relatively okay. It's just a general thing. So like I said, so then if I take the there is a map from a Korean kg. This is just representations of G. So you can make any representation of G, make a trivial bundle over your X. So that means this is some ring. Means that the spectrum of this ring maps to the spectrum of this ring. But what is this ring? These are just group up to conjugation. Because these are just characters. The elements in this representation, their characters are distinguished group after conjugation. Means if we think of this as a scheme, this will sit over that. And that is to say, here this sits over symmetric functions in this variable a. And what does this? How does this sit? So here I sit this. Here I think this. Here are my a's. These are a's up to permutation. These are symmetric functions. And what is, well, I didn't say it, well, I guess I stated. I stated that the theorem that the K-theory of any Nakajima variety is generated by tautological bundles. In particular, for projective space, that means that the K-theory is generated by a single variable, namely that variable L. No, that is trivial because the K-theory of T star and Pn are just trivially the same. Yeah. So there's this coordinate L, and this coordinate L can take n different values. Right? That just says that just my scheme, it looks like this. It has n different values. Namely L could be AI, A1 inverse. L could be A2 inverse. And so for L could be AN inverse. And now there's something kind of amazing about this picture. Namely, we can ask, what is the fiber? So this is a map of schemes. You can ask, what's the fiber over a point? Well, of course, that depends. Since this is an intersection of just intersection of copies of this, that depends on whether some of the AIs are equal or not. So there's some stratification here downstairs where this AI is equal to AJ. And so then the fibers, so maybe, sorry, this is a bad picture because the center of that, the center of that sits here, okay? They intersect, these guys intersect on this sum of this AI equal. The moral of the story is that the fiber over any point G, so if I take the fiber, if I take an element G here, the fiber of that is in fact the K-theory of the fixed locus. If I take a very general G, this is a general statement. So if I take a very general G, when means all these AIs are distinct, then the fixed locus on projective space will be n distinct points. And the K-theory of n distinct points is just n copies of well, integers or whatever your coefficients are. And this corresponds to the fact that this is n different. When they come together, the fixed points jump. Like when two AIs come together, then you get like a P1 worth of this. And then correspondingly P1 for P1. So if they two came together, here you're going to get this double numbers. You're going to get a relation of the form like 1 minus L squared equals 0. This type of relation. That is a relation in non-occurrent K-theory. This is non-occurrent. This is a relation in non-occurrent K-theory of P1, because when it's non-occurrent, you forget these variables, and in P1, there's a relation that's like this. And it's also, of course, this relation in homology of P1. Homology of P1 is an algebra with 1 and some generator. Right? And so then this brings a very, very important fact. There's something called, there's something kind of, the fact that this scheme, if you think of this as the scheme, I mean, of course, if you know what that scheme is, away from whenever these guys come together, of course we know what it is in general. Right? I mean, it's clear, right? It's just, that says, so there's, you can look for, and the way to say it is we can, oh no, this is really bad. So, and the way to say it, we can look in the spirit of in the spirit of formula you already look, you can look for so maybe I'll write it like this. So there is a map. You take a K-theory of, so let's for concreteness, so in the theories we're discussing, we can just might as well take, let's take a maximal torus, and that'll be better. So in the theories we're discussing, the while symmetry, you can observe it after the fact. We don't really use it in any essential way. If the fact that this is symmetric in AIs, it's some feature, but we don't really use it in an essential way. So let's take a maximal torus, and let's take an inclusion of the fixed locus into my ambient variety. Right? So that by the exact sequence I wrote, this goes to the, so this is a T, let's take the T covariant K theory of that. So by the exact sequence, this goes to X minus the fixed locus. This goes to 0. And the kernel here is some kind of K1 of, which I didn't define, but doesn't matter. And so what is this picture here? The picture here is that if I take all these copies and just take them apart, this would be this guy here. So this object here, the current K theory of the K fixed locus is just all these guys, but now just taken apart. Right? You can think of this. These are just like a linear subspace or rather subtor, right? And you can just take normalization, just take them apart, and that is this map. Or rather, pullback is the map. No. Spec.
So T does not contain the G-mod computation. T-mod double is.
Yes. I'll take T and G, and then we can also take G-mod. Right? So that says here it says that if we take them apart, these two schemes are isomorphic except on some codimension variety. And so the general theorem of Thomason, I guess, is that this guy and this guy are torsion. Means they sit. These are some shifts that sit on some subvarieties. So we don't really care about them so much, because in the end we want to compute. In the very end we want to compute some character. And it's a character. It's some function. Maybe a polynomial or rational function. And if we know a polynomial or rational function outside of something which has so in the end we want to compute, like I said, in the end computation everywhere is some character, some function of this group variables. If we know that function outside of some subvariety, then it doesn't matter. Then we know it everywhere. And so the typical argument that says that you argue modular torsion means you argue modular things supported on some subvariety, and then this becomes just an isomorphism. Okay. So now my 3 minutes over time, I need to state the most important theorem of the talk, is that this is in fact you can write a specific representative. So if I want to know, suppose I have a vector bundle, a covariant vector bundle on X, and I'd like to find a specific representative on the fixed locus that pushes forward to this vector bundle. Right? Then so I need to write. So how do you compute? Maybe I'll say how you compute it. You compute it using, so if X, the argument only works if X is smooth. If X is smooth, then you have if X is smooth, there is a pullback map. And if you compute push forward and pullback, if you compute them, like if you compute the push forward and pullback, the kind of computation you need to do is this exactly the Kazul complex computation that we did. What did we do? We took the origin in the vector space. We took the structure shift of the origin, that is to say, we pushed forward the shift from this origin to the vector space, and we took its resolution. Resolution we can pull back, and so then we can compute the result of computation push and pull computation. And so when we compute the, so maybe I'll write it like this. If I have smooth subvariety, okay, if I have a smooth subvariety Y inside of X, and I want to, so maybe I is an inclusion of Y to X. If I want to pull back the push forward to Y, so what I'm going to need, I need to resolve, when I compute the pullback, I need to resolve the structure shift of Y by shifts on X. And this is the Kazul computation that we did. So that would be the exterior, like the exterior algebra with the minus signs of the dual to the normal bundle. Take the dual to the normal bundle. We had the dual of the vector space itself. The vector space itself is promoted to the normal bundle. There's a normal bundle too. And so then when you thank you, Pasha. And so if we now want to write a representative for V, as pushed forward from the fixed locus, then what we will need some expression. Then when you multiply it by this guy, then you're gonna get your bundle back. And so then the expression is that this is you have, if iota is the inclusion of the fixed locus into X, then your bundle V, that is the push forward of what? You have to, when you pull it back, you have to get your bundle back, and you have to compensate for this. So that means you put your bundle. So there was a bundle restricted to the fixed locus, and you divide by the character of the exterior algebra. Usually, so in the situation with instanton moduli spaces, the fixed locus is just points. And then when you have with this are points, this is what you're dividing by is this exactly the kind of denominator we just wrote down for this projective space. So this is for 4 points. What you're going to get 1 over the product of this kind of 1 minus kind of AI inverse type of thing, where the AIs are the weights of the action in the normal bundle. And so these are the box, since I wanted to get to the formulas, these are the box counting formulas. Because what does it say? Let's say if I want to typically in the end we want to push it for, like I said, the end result, some kind of integration. You push things forward. So if I want to push forward V, I might as well, and I know I can in fact push it, and there's V is represented by the push forward from the fixed locus, then I might as well just compose this to push forward. And so then in the end I just get integration over a fixed locus. And the fixed locus's point, I just get summation over points with this kind of denominators that you get. And so, but to know what are the terms in the summation, you need to know what are the weights of the action in the normal bundle order. That's the basic computation in the problems that you need to. This is something you need to compute. Okay, well, oh no. So we have to wrap this thing up. Yeah. So that's all. Yeah. Uh-huh. Right, but in here we're doing everything in algebraic geometry. Everything is oriented somehow. Yeah. 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 Okay, let's break quickly since we need to prepare for this next set of lectures.